Hi, welcome to our presentation on graph convolution networks for fusion of RGB-D images. My name is Alexander Swerdlow, and I'll be presenting with my partner, Puneet Nayar. And in this project, we explore methods for fusion of RGB-D and point cloud features. We compare two graph-based networks with an image-only method, and we achieve significantly higher accuracy on a material prediction dataset compared to the original authors. So first, we use Deep10 as our baseline image-only network. Our model used convex as the backbone, followed by a convolutional layer, and then an encoding layer, and then finally a fully connected layer for prediction. This encoding layer is similar to an attention mechanism, as it performs dictionary learning and weights each residual compared to the dictionary keys based on a smooth softmax assignment. Next, for our first graph network, we implement a dynamic graph CNN, or DGCNN. This is from a paper that introduced the edge convolution operator and the concept of a dynamic graph that changes at each layer. And the edges for any node at a given layer consist of its k nearest neighbors in feature space from the previous layer, so that will change for each node at any given layer. And we use the max operator for our aggregation function and a shared MLP where the node features and the difference of the features compared to its k nearest neighbors in feature space are concatenated. And then below we see an example structure of a DGCNN. This is not the exact structure that we used, as we had many different variants, but it's just to give you an example. Next, we have multi-neighborhood graph convolution. And this is based off two so-called attention graph convolution modules, one for Euclidean position and another one for node features. And again, attention is not the standard formulation here. The values are the node positions or features themselves. And these are weighted based on the output of what they call a dynamic filter network. And this is simply the difference of a node feature or position compared to the other node feature or position that we're comparing it to. And these nodes that we're looking at are chosen differently for the Euclidean and feature neighborhoods. So we use a radius-based assignment for the Euclidean neighborhood and KNN for the feature neighborhood, which intuitively makes sense because a radius doesn't make as much sense in feature space, but it makes perfect sense in Euclidean space. It makes the network easier to reason about. And then again, we use max as our aggregation function between the two AGC modules.
The second network architecture that we explored is inspired by the same group that proposed multi-neighborhood graph convolution. It actually consists of three separately trained networks, where the first one extracts 2D features using the weights from some pre-trained backbone. The authors used a ResNet while we tested with Convex. The second network uses the multi-network graph conv operation along with nearest voxel pooling layers to extract 3D features. And this nearest voxel pooling operation is a modification of typical voxel pooling, where after creating centroid in each voxel, points are then reassigned to their nearest centroid, and the centroid position and features are recalculated based on this reassignment. Then a one-by-one convolution is used to match the feature size of the 2D and 3D features. And these, once they have the same feature size, they're fused with another modified nearest voxel pooling step where the 2D and 3D feature averages are concatenated for each centroid. And then lastly, these fused features are passed to a final classification network. The dataset that we chose to evaluate our networks on is the GeoMat dataset, which consists of 19 different materials from real-world sites. And each example includes an RGB image as well as sparse depth data. So we project this to a 3D point cloud using the provided camera intrinsics. And in terms of pre-processing, we normalized each RGB channel and also normalized the positions of the points in the point cloud to be between -1 and 1. For data augmentation, we also used random flips and rotations on both the 2D and 3D data, and also used dropout and random 3D cropping on the generated point clouds. We tested a variety of different implementations, so 6 representative networks here. The first is our RGB only baseline using the convex backbone. We also tested 4 separate DGCNNs, one which uses only the depth data, one which incorporates RGB features for each node, one which incorporates the features from the convex backbone along with RGB-D features, and finally, one lightweight version of the third DGCNN, which has far fewer parameters. And then finally, the last network is the 2D, 3D fusion network. So here are our test results for our implementations. The baseline deep 10 network achieves around 68% accuracy, and each of the 3 DGCNNs has an accuracy of 38, 61, and 76%. And the lightweight version also has a comparable 75% accuracy. And our best network was the 2D, 3D fusion network, which had just above 77% accuracy, which is actually 3% higher than the best result achieved by the group who created the GeoMat dataset. And overall, we noticed that using just 3D features alone doesn't give great results, like in version 1. This is probably because a lot of the materials in the dataset have similar 3D geometry, and the sparse depth data that's given isn't high resolution enough to capture any differences. But in both our DGCNN and fusion networks, combining the 2D and 3D data led to large improvements and gave promising results. For more details, please refer to our blog post. Thank you. Also, for anyone who's interested in replicating our results or testing other models, we want to give you a quick overview of how you can do that. Here is our repository, which we have linked in our blog post. We provide setup and install instructions, as well as a link to where you can download the dataset and instructions for how to or where to place that. The models and scripts to train them, and all the script to train these models are in these 3 folders: Deep 10, DGCNN, and Fusion. And if you want to train any of these, we also have instructions on how to do that here in the README. We also provide a demo environment in the Colab folder, and we provide a notebook here. So this notebook will install any dependencies and also download a smaller version of the dataset. There is an example DGCNN model here, which can be replaced with one of the other ones from the folders I mentioned before, or modified however you like. And we also provide a training and test loop for that. So if you want to test in a smaller environment, then you can do that in here. Thank you.